Let us welcome our next speaker. It is a pleasure to introduce Professor Matej Brešar from University of Ljubljana and University of Maribor, who will tell us about Jordan homomorphisms.
Morning, can you
Please.
hear me?
Yes, we hear you.
It seems I cannot share. It's written that someone else is sharing.
Try again.
Yeah, it should work now. Can you see my screen now?
Yes, we can see your screen.
Oh, okay. So, um, first of all, I would like to thank for the invitation, and at the same time, I would like to congratulate the organizers and express my admiration for continuing this series of conferences in these difficult times. I believe that this is very important for the present and maybe even more so for the future. Okay, so as you can see, I will speak about Jordan homomorphisms, and I should say at the very beginning that there will be quite a substantial overlap with the talk by Efim Zelmanov, which was given yesterday in the afternoon. So partially I will speak about the same things, but perhaps from a slightly different perspective. So I will spend maybe half of my talk for introducing the concept, the problems, the motivation, and the history. So let me start, and then in the second half, I will speak about the new results. So let me start by the definition, which of course was given yesterday. So if we have two associative rings, R and R prime, then an additive map between them is called a Jordan homomorphism if it preserves this operation xy plus yx, which is called the Jordan product of elements x and y. Actually, the definition I gave is incomplete because one also has to require that phi preserves this additional property, which you can see here. However, under the assumption that the ring R prime is 2003, this second equation follows from the first one. And very often in this context, when studying Jordan maps, we assume that our rings are 2003. So there's not much difference. And besides, in this context of 2003 rings, the definition can be equivalently stated as that phi preserves squares. It's very easy to see that this is so. Okay, so what are the basic examples? They are quite obvious. The ordinary homomorphisms are also Jordan homomorphisms, and so are the anti-homomorphisms, the maps that reserve the order, like the transpose of matrices. And the problem that we usually study is whether all Jordan homomorphisms are of this type, so homomorphisms, anti-homomorphisms, or their combinations. I should add that this definition of a Jordan homomorphism makes sense not only when R is an associative ring, but also when R is a special Jordan algebra. I will recall the definition very soon in the next pages. But before that, let me warn you that sometimes I will speak about algebras and sometimes I will speak about rings. This shouldn't bother you. It is just for some traditional reasons. Sometimes one word seems more appropriate than the other, but there's no much difference. So you can just ignore this and think of algebras all the time. So to put everything into the right context, into the proper framework, I will first recall a few general facts about Jordan algebras, because one way of looking at Jordan homomorphisms is that that they are a part of the Jordan theory, the theory of Jordan algebras and related structures. So what is a Jordan algebra? This is a non-associative commutative algebra, which satisfies the following axiom, some weak sort of associativity. In fact, the basic example of a Jordan algebra is just an associative algebra in which we replace the given ordinary product by the Jordan product. So xy plus yx, and we usually denote this algebra by A plus. So what is then a Jordan homomorphism between associative algebras? This is nothing but the homomorphism of the corresponding Jordan algebras. So that's where the name comes from, obviously. Now, these Jordan algebras of the type A plus are certainly not the only Jordan algebras. Every linear subspace of A plus, which is closed under the Jordan product, is also a Jordan algebra. Such Jordan algebras are called special, and there are rare, but there exist also those that are not of that type, that are not directly subspaces in the sense of associative algebras, and they are called exceptional. The very basic and most important example of special Jordan algebra is the linear space of all symmetric elements or Hermitian elements in an algebra with involution. So like symmetric matrices, for example. So this linear space is obviously closed under the Jordan product, but in general not under the standard, usual given product. The basic example of an exceptional Jordan algebra is the Albert algebra. This is a certain 27-dimensional algebra consisting of, as you can see here, 3 by 3 self-adjoint matrices over the octonions under the Jordan product. And it follows by the work of Zelmanov that this is in some sense also essentially the only example. It's not, of course, true, but all known examples are somehow related to this one. There's another example that should be mentioned here. This Jordan algebra is relatively easy to deal with. Every symmetric bilinear form on the vector space gives rise to a Jordan algebra. You can see the definition here. It's not relevant for this talk, so I will not comment further on this. And there is a well-developed structure theory, classical theory of Jordan algebras, which, roughly speaking, shows that algebras of this type, which were mentioned so far, are also under certain conditions, of course, the only ones. And everything started with the paper by Jordan, von Neumann, and Wigner in 1934. And the most general results were obtained by Efim Zelmanov, who showed a result of that type just mentioned for prime non-degenerate Jordan algebras. So essentially, in some sense, these four types are also the only types that are worth of considering. Okay, so this was one point of view why to study Jordan homomorphisms. They are natural because they are homomorphisms of related corresponding Jordan algebras, but there is another reason. So Jordan homomorphisms just appear across mathematics in many different areas. They are very, very natural. Let me try to explain why. So why do we study homomorphisms? We study homomorphisms, the ordinary homomorphisms, because, as we explain to students, they preserve the structure of rings and other algebraic structures. So if we want to relate to rings, then we need the notion of a homomorphisms. But anti-homomorphisms also preserve the structure. Okay, not exactly. They preserve everything what's left-right symmetric. So that, for example, they may map left ideals to right ideals, but still we can say that they preserve one-sided ideals. So they are equally natural in some sense, or almost equally natural. And no, we can combine them. So we decompose our ring into two factors, both of them. And on the first component, we take a homomorphism. On the second component, an anti-homomorphism. Let's call this a direct sum of a homomorphism and an anti-homomorphism. And these are also maps that essentially preserve the structure. But so do the more general Jordan homomorphisms, because this direct sum of homomorphisms and anti-homomorphisms are their basic examples. Um, so there are many problems in mathematics, and actually there's a whole branch of mathematics called linear preserver problems that studies linear maps that preserve certain products or preserve certain subsets of algebras, etc. And usually the usual conclusion is that such maps are Jordan homomorphisms. Um, I think that, and people are usually happy with this conclusion, but I think um, they shouldn't be entirely happy because they start with associative algebras and then they somehow the result is okay modulo the Jordan structure, modulo the Jordan theory, and so one has to come uh, to the final conclusion. And so we can study Jordan homomorphisms to try to obtain their form. And I will now state some classic theorems. The first mathematician who has considered them was a Spanish mathematician, Ancochea. The theorem which you can see here is due to him and Kaplansky. Actually, this formulation is due to Kaplansky, but Ancochea was very close. So Jordan isomorphisms between finite dimensional simple algebras are just isomorphisms or anti-isomorphisms. The famous Chinese mathematician Hua um, proved at about the same time, so that you can see the 40s, a long time ago, the Jordan automorphisms of division rings are also only automorphisms or anti-automorphisms. And he introduced the famous Hua identity, this paper. Um, Now, Jacobson and Ricard slightly later extended this to domains, so domain ring without zero divisors. So it's enough that the second ring has no zero divisors, and then the only Jordan homomorphisms are homomorphisms and anti-homomorphisms. Herstein proved that every surjective Jordan homomorphisms onto a prime ring is also just a homomorphism or an anti-homomorphism. Now, the next result, which is due to Jacobson and Ricard from 1951, is of a different type. So Herstein's result, quite a known famous theorem, imposes the condition on the second ring or R prime, but here Jacobson and Ricard they impose the condition only on the first ring R, and they assuming that this ring is a ring of n by n matrices over any unitary ring, commutative, non-commutative doesn't matter, then Jordan homomorphisms from R to any other rings are sums of homomorphisms and anti-homomorphisms. Here I should, in this final remark here, I should explain that when speaking about sums, we also assume that these images of phi 1 and phi 2 are orthogonal in this sense. So yesterday, Efim Zelmano talked about this, and he called these subjordan homomorphisms standard. Now, a theorem also very classical from a different area, but also from the same period. And this is a perfect example of what I was speaking before, how Jordan homomorphisms simply naturally occur in mathematics. So Caddison, this is a very famous result in sister algebra theory, proved that bijective linear maps between unital sister algebras preserving unities are isometries if and only if they are Jordan isomorphisms, which also preserve the involution. So it's a really beautiful theorem. So it connects this geometric condition, isometry, with the algebraic condition, being a Jordan isomorphism. And Caddison also, in this important paper, proved that if one of the algebras is von Neumann, then these Jordan homomorphisms are sums of homomorphisms and anti-homomorphisms. There are other results on Jordan homomorphisms, not only those that are defined on algebras, but defined on other special Jordan algebras. And the one of special interest are symmetric elements or Hermitian elements. So in fact, this special Jordan algebra, so the Jordan algebra of the type R plus is also of that type. So Efim Zelmano spoke about this. So this is a very general. This is just what I wanted to say. This theorem also mentioned yesterday in Zelmano's talk. The original version due to Martindale and then extended to Jacobson shows that if we have a ring with three orthogonal symmetric idempotents whose sum is 1 and each of them is full. The ideal generated by this idempotent is the whole ring. Then Jordan homomorphisms from symmetric elements can be extended to homomorphisms. You may wonder why there are no anti-homomorphisms here, and the answer is simple. So if you compose the anti-homomorphism with an involution, you obtain a homomorphism. And the involution acts as the identity on symmetric elements. Okay, and then the last page, which is about the history. So the McCreeman in '89 used the Zalmanov methods, so from the structure theory, which I mentioned before, to obtain this another type of result for Jordan homomorphisms. So Efim Zerman also mentioned this theory. He was somehow more insightful, but the page you can see here is more technical. What Efim mentioned yesterday, that using the tetrad eating method, which was the basis of his method, which produced this structure theory, and also the structure theory of Jordan algebras later led to the solution of the Burnside problem in group theory, so very famous result. That one can also study Jordan homomorphisms by this. Okay, so you can see some complicated polynomial here. Do not pay much attention about it. It's not the only possible polynomial. It is just the fact that there exist polynomials. This particular one has degree 48, so big polynomial somehow, such that if you take the ideal generated by the evaluations of this polynomial, you can say something about Jordan homomorphisms. And here is the McCreeman's result that if you have a special unital Jordan algebras contained in symmetric elements, and this Z of J, Z is McCreeman calls this Zelmanov ideal, is equal to J, then Jordan homomorphisms, as usual, can be extended to homomorphisms. Okay, and now I finally come, I still have 10 minutes, so I have to hurry, to the new results. I have to say that although it's not obvious from what I will speak about, that these new results are connected to Ukraine. On the first day, Oksana Bezushchak spoke about uh, problems related to these ones on infinite matrices, algebras of infinite matrices, and then um, um, later with Efim Zelmanov and Irina Kashuba, they studied these problems in a more abstract context of uh, algebras with idempotents. Um, and About a year ago, in the middle of the summer, I received an email from Efim Zelmanov asking me some questions related to my old works about this. So then I looked at my old papers and found out that there are still some natural open problems, and also that when I was working on this many years ago, that I overlooked some things, and so this led to two papers which I will now present, and they are somehow originated from what Oksana talked about on the first day. So it gave me a very good excuse to return to Jordan homomorphisms, which have always been one of my uh, favorite topics, and also by chance, my very first papers from the end of the 80s are about Jordan maps. Okay, so I will now first speak briefly about this first paper, which was just published. Okay, K will denote the commutator ideal of R. It is an ideal generated by all commutators. And the problem which I will study now is whether a Jordan homomorphism is the sum of a homomorphism and anti-homomorphism not on the whole ring, but on K. Why on the commutator ideal? This example here, I have no time to comment it. But it shows that under relatively mild assumptions, you can construct um, uh, a Jordan homomorphism on a given ring, on some classes of rings, which are not standard, do not arise from homomorphisms and anti-homomorphisms on the whole ring, but only on the commutator ideal. So if you want to have a general result, it's hard to expect that you can find some very nice class of rings where you can have this expected result, but it's better to focus on the commutator ideal, which is the most non-commutative part of the ring, and somehow natural in this context. So this is the definition, which is the basic of this paper. A Jordan homomorphism is splittable if the ideal generated by this type of elements has trivial intersection with elements of this type of elements. So if the first ideal is zero, if and only if I is a homomorphism, and the second ideal is zero, if and only if I is an anti-homomorphism, obviously. This looks as a technical condition. Well, it is a technical condition, but this proposition here shows that it is natural because there are many natural examples where one can show that Jordan homomorphisms are splittable. I will not comment because I have to hurry. So the main result here states that of this paper I'm presenting, that a splittable Jordan homomorphism is the sum of a homomorphism and an anti-homomorphism on K. And there are several examples showing that the restriction to the commutator ideal case is natural in this context. A few corollaries. So if a ring is semi-prime and phi is surjective, then phi is the the sum of a homomorphism and an anti-homomorphism on K. Then if a ring is reduced, it means no non-zero nilpotents. Then surjectivity is not necessary. And this final result here, the third one, the third corollary, is a generalization of Caddison's theorem on the sister algebras. So somehow there are more corollaries, but let me just conclude this by saying that this somehow paper shows, first of all, that it is natural to consider only the restrictions of Jordan homomorphisms to commutator ideals, because this is because of examples. And then this notion of a splittable Jordan homomorphism enables a unified approach to this problem. So it is a technical condition. And the truth is that it's not always easy to check whether a Jordan homomorphism is splittable. But still, what I have shown is that some new results can be obtained. I'm not claiming that there are some, these are spectacular results, but they are new and they somehow unify several of the classic theorems. Now, in this very last part of my talk, I will speak about the joint work with Efim Zelmanov, and he presented the two theorems I will present now also already yesterday. The paper is close to be finished. It's more or less written. Now I will assume again that we have algebras, not rings, and the fields should have characteristic not 2. Okay, and so our first result states that if a unital ring is such that it coincides with its commutator ideal, then surjective Jordan homomorphisms are sums of homomorphisms and anti-homomorphisms. What does the notion, what does the surjectivity means here? It simply means, because R prime here is an entirely arbitrary associative ring, it simply means that the image of phi is an associative algebra. We need this condition, although we are not sure whether we really need it. And there are, among corollaries, I'm mentioning only one which somehow suggests that the commutator ideal is very natural here. Because if the ring is not equal to the commutator ideal, then we can extend it by the tensoring by some commutative algebras, and then we can produce a Jordan homomorphism that is not standard on this extension. And the very last result, which is philosophically close to McCrimmon's one I mentioned before. So again, we can find T ideal in this McCrimmon's result I mentioned. This was a very concrete T ideal generated by a concrete polynomial, but this doesn't really matter. So this T ideal such that if we have a Jordan homomorphism on symmetric elements, then we can extend it on the evaluations on this T ideal to an associative homomorphism. And this T ideal is relatively big in the sense that every element of the T ideal of polynomial identities of 2 by 2 matrices is nilpotent modulo G. So it's somehow concrete T ideal. So the advantage compared to McCrimmon's talk is that we do not assume that it is this equal, this T ideal to the whole ring. And a similar result holds for Jordan homomorphisms defined on R. And also, as if you mentioned yesterday, an example shows that, I, I forgot to mention because I was hurrying, we have to assume that the image of I has trivial annihilator, and this turns out to be necessary. So it's somehow this result is optimal. Thank you very much.